This video is the second part of a mini series for feedback for each loops. In this video, I'll continue on with basic concept number 4. So the next one is basic concept number 4, which is a little bit more practical and something that I use the feedback for each loop a lot is to modify the topology of my geometry. And we're going to start off with the same grid, with the same simple grid that doesn't have any topology. And I'm going to position the grid so that it's right in the 0, 0 position. So I don't have to worry about the negative coordinates. And this just makes my life a lot easier. So I'm going to set this to match size to min min. And since there's nothing connected to the second input, it will just use the world axes as a reference to compare. So it's going to be set to the minimum of the world axes, which is 0, and the minimum of the z-axis. So it'll be set to the minimum of the x-axis and the minimum of the z-axis. And let's take a look here. And you can see that the grid is positioned right 0, 0 here. And everything going above here, those are all positive values going in both directions, here and here. In the x direction, so this would be the x direction. In the y direction, these are all positive values. I'm trying to avoid everything down here, everything over here, only going up here and here. This is all positive numbers, and this is just makes my life a lot easier, and I don't have to deal with the negative coordinates. Next, we're gonna feed this into a new feedback for each loop. So let's drop down a for each number loop, connect this up. And I'm going to turn this into a feedback for each loop. So merge each iteration becomes feedback for each. And I'm going to lower down the iterations to begin with to 3. Next, I'm going to come over to the for each begin node. And I'm going to change this, instead of fetching the input, to fetch the feedback, because that's what we really were going to be talking about in this video. Now for the functionality. Now we're going to put in the meat. More interesting things is that I'm going to slice this up. So I'm going to put down a knife. And what the knife node does, it modifies the topology of the geometry without changing the geometry. So a quick example. I have a grid. I'm going to, again, the same 2x2 grid, the same plane grid. I'm going to put down a knife. This just creates more topology for me. I'm going to use the manual input to show you what it's actually doing. Position the knife so that it's going to slice sideways. And you can actually start to see the line that it's forming. It's creating more polygons. It's creating more points on our grid. So we began with 4 points. We began with 4 points on the grid. After we applied the knife node, we get more points. Get 6 to be exact. And it's added this line here. It's added this line right here. And it's actually cutting the geometry. But it's not cutting through the geometry. It's just creating more topology. In order to show you that, we'll move this geometry around. Oh, I don't need to select that. I just want to select the face of the geometry and then move it around to show you that it's still welded together. You can see that it's still welded. So it's not changing the geometry shape, but only creating more topology, creating more polygons, more points. And topology comes in really handy when you're doing procedural modeling in Houdini. The knife combined with the feedback for each loop is pretty handy. And this is one way that I use it for. We're going to slice this grid up. We're going to slice it procedurally. So first of all, I want to slice it in the x direction, in the positive x direction. So we're going to slice it in this direction. And what we're going to do is we're going to tell the knife to cut in this direction. We're going to cut this grid. We're going to cut it in slices, sort of. But each time we're going to cut it half. So I'm going to be splitting first the grid in half. It'll be like split down here in the middle. The next time, it'll be half of the half. So the next split will be down here. And then the next one will be half of the half. So the next split will be down here, and so on, so on, so on. So that's what we're going to be using the feedback for each loop. And this is something that you can't easily create with other nodes. This is perfect to demonstrate the power of the feedback for each loop. First of all, we need the position of the knife to be pointing in the right direction. And the direction is going to be in the positive x direction. We're going to change this to 1. and it's not going to be upward, so this is going to be 0. So we're facing this direction. We're going to be cutting in this way. The next thing we want to configure is where will we start cutting? And that comes into the origin. Well, where do we want to start? This actually works out fine for us because it starts in the origin position, which is the origin of the world. And because I had moved the grid to the origin of the entire world to begin with using the match size over here, we're conveniently already on the origin. Our grid is conveniently placed on the origin, which is this right here. The next thing we want to configure is the distance of the knife here, how far to cut each time. So we want to cut half of it, and for this I'm going to be using a simple Houdini expression. It's called the B box, and what this does is it grabs the dimension of whatever node you want, and we want the dimension of the current node, or the one that's connected to the knife, which is the current grid node. So that would be 0. That's the input 0. I'm going to have input 0, and what do I want? I want the size of the X of what it's spanning, and that would be D underscore X size. So that would be the width size of this grid. It so happens that this is a square, so it doesn't matter which the X or the Z. It's a ratio of 1 to 1. It's just a perfect square. And then now we have that size, but we're not going to cut the entire size starting from the origin. We want a fraction of it. I wanted half, as I said at the beginning. So I'm going to take this number and I'm going to divide it by 2 because that's what I really want. I just want half, to always cut this grid in half and repeatedly cut it in half. Now I have this turned around. Now I want to cut the next part in half. The new face that we've created, this face, and I want to cut this in half. But how do I actually get this primitive? Well, the knife node has something very convenient. It can create groups for us. And what I want is to create a group to identify the part that we've cut. And we have the above plane is what we want. In order to be sure that that's the plane that we want, I want to drop down a group node. And this group node will only be for visual purposes. So I'm going to be coloring this black. It will not affect our geometry at all. Specify above plane here. And we can see that it is indeed selecting the next face that we have cut. And this is useful because I'm going to keep telling the feedback for each loop to always cut the next plane. So we don't end up cutting back and forth. We're always going forward. What we learned from basic concept number 3 is that the initial state is very important. So I'm going to show you the wrong way of doing it, sort of. And then I'll show you how to set up the initial state. So just like the poly extrude, I'm going to tell the knife node to only cut the above plane. And how do we do that? We can specify the group up here. So it'll always cut the next plane. But let's give this a try. Look at the result. It's not doing anything after I place the render flag here. This is not being cut at all. It's just not doing anything. And that's because we don't have the correct initial state. This over here is not getting the right input. It's not starting in the right state in order to trigger anything to kickstart the entire feedback for each loop. That's what the knife needs. In here, the knife, we have specified only to cut the group above plane, but we have to begin with, for the first iteration, we need to kickstart it with an above plane. So let's move all this up, and I'm gonna create an initial group and assign it to our initial geometry and call it above plane. So this will kickstart the entire feedback for each loop. Let's see our results, and it is indeed cutting it. This feedback for each loop is going through it 3 times, and it doesn't seem like I'm getting 3 cuts. It just seems like I'm getting 1 cut. So let's start off with the first iteration. Let's go back a bit. Now, where is the knife gonna cut the very first time? It's cutting in the correct spot now. But let's run through this. The knife is cutting at the origin spot at a distance of 5. And it so happens that it's right here. So this is it. Where's the origin? The origin is right here. There's the origin spot. And going 5 units up will get us into this line. And that's how we're cutting this one line. Okay, that makes sense. So let's turn this up. Let's turn to the next iteration. Increase the number of iterations. This is the second iteration. Why isn't the second iteration cutting in the right spot? Well, let's run through this again. Now, the knife, the origin is still in the 0, 0, 0 position. So that would be here. Then we're cutting 2.5 units over, which so happens to be right here-ish. And we're cutting in the middle of nowhere. So we really have to move, not only the distance has to change, the origin has to change as well. The origin has to depend on the number of iterations to move it forward, or it has to start on where the geometry starts more precisely. We have to position the origin over here. This needs to become our new origin. And in order to cut in the right direction, we gotta move it. We gotta be moving this over here. And then our new cutting line should be somewhere around here. The distance, I think, is all right because the distance is always dependent on the new primitive. And the primitive is always changing. It's always being half of the new face. So I think that works out fine. It will always give us the right distance. We only have to fix the origin and move the origin forward to the lowest x value of our new primitive face. And how will we do that? Well, we can always use B-box. So the x direction here, we're going to use B-box again to get the bounds. And I want the bounds of, again, the first input, our new geometry, whatever is connected to our first input, which is the grid. And I want the dx, but min this time. I want the minimum position of the x value. And it looks like we're cutting in the right direction now. Let's see what this results in. Now I'm going to keep increasing the iterations to see if this is working. Okay, it's indeed cutting in the right direction. You can see that it's getting smaller and smaller and smaller and smaller and smaller. Okay, we're getting somewhere. Now what we need to do now is to merge whatever we split. In order to get the correct values for the knife, I had split the geometry over here. So this split, now we have to join that back in. Merge in the knife and then merge in our split. This will be our new result. Okay, we can instantly see this is working. Now I'm going to modify the iterations to just double check. We start off with no cuts. The first cut, second, and it is cutting half, 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 half. Now the beauty of this is that we can now procedurally modify our input data. And that would be the original grid up here. So what I want to do is change the size of the grid. So this is something that we already have functional, and then we can change certain parameters to get a different geometry. And I want to stick a transform node here, and I'm going to change the size of the grid, and I want to stretch it up. Now, since we have a larger input data to work with, I'm also going to increase the number of iterations for the feedback for each loop. Now it's just cutting more and more and more here. So that's not helping much. Since the half is too much, I want to modify this just a bit. Let's go back to the knife and I want to go to the distance, and instead of cutting half, let's cut something like, let's do something like 10. Okay, that seems a bit much, but let's also increase the number of iterations. So this allows us to cut with more iterations now. And this looks a lot more useful. It looks even better when you map the area to a color node. I'm going to drop down a measure node so I can get the area of each square. Now we check out the geometry spreadsheet here for the primitives. You'll see that we have an area column here. And that is the area of each primitive rectangle square in our little strip here. Drop down a color node. I'm going to map the color of the primitive, of each primitive, to a attribute. And what attribute we want is the area. So we can actually map the area to a color. And we can get a deeper color, a darker color, or a lighter color, depending on what area, amount of area we have. So I'm going to change this from black to red, the black and white to red to green. Green down here. Let's put this to red. Less area has will be red, and the more areas you have will be green. And you can instantly see it changes color right here. And you can see the speck of red just because that has the least amount of area. There is another thing that you need to be aware of. This range 0 to 1 is not capturing all the data. We're actually losing a lot of data because our area is ranging from has a larger range. Is that down here in the geometry spreadsheet? If we click this, we'll see that the maximum area, the largest area you have is 63. And we're mapping everything from a range of 0 to 1. This range is not capturing all the data. Realistically, we want to put this up here to 63. So that would capture more data. But I want to make this procedural. I don't want to keep modifying this color node in order to get that maximum data. There's actually a way to get that number so let's come down here. We have a measure node. And all our information is in this area attribute. But I want to know the largest area attribute value. Let's drop down an attribute promote. So there's no easy way of getting the largest number in the spreadsheet, but we can always use the attribute promote and promote the largest number to a detail. Detailed attributes, in detail attributes, you can only have one instance of that attribute. So that makes it perfect because there's only one largest number. There's only one largest area. You can't have two largest area values. There's only one largest. So we're going to change this from primitive. That's what we're starting with. And we want a new one called to details. Promotion method. Well, we want the largest one. So we want the maximum here. We want the area. And now we want to change the name. So we're going to change this name and it's going to be max area. But we're going to keep the attribute. I don't want to delete it. Well, you could. It actually doesn't matter because we're not going to be using, this is branched off. You can see that this here is branched off from here. This color node is still reading all the data, is still getting all the area data over here. It's always going to exist over here for the area data. Will always exist for the color node because it's always here. The code has been branched off, sort of. Now, I like to do a good habit is to put down a null node and put down the name of the attribute that I'm looking for, which is the max area. Come into the color node here. And I'm going to plug in a Houdini expression to get that data, to get that max area data. And what I want to do is the details, because the max area is stored in the details attribute. So we need a detail function. Detail function, what's the node? What's the name of the node that we want? Well, okay, if we're going to start pointing nodes, we need a string. And we need to start off with a dot dot. And this, what the dot dot means is that we're going to go above this node. It's some other node other than the color one. It goes one step above. It's sort of like your folder system. I'm not in this folder. I want the one above this one. And which is the one we want? Well, I conveniently named it max area. Close it off. So that's the node location that we have. Name of the detailed attribute, which is also called max area. So if you name everything, if all your names are aligned, it makes it super more convenient and easy to get stuff. So the last input over here, the last input is the attribute index. And that's just always, that's 0 in our case, because this is a scalar value. If this was a vector and you wanted the y or the z, then this number would indicate which component you want. It could be 0 for the x, 1 for the y, and 2 for the z. So it would indicate which component. And in this case, this is a scalar value. There's no component. It's not a vector. And we just want the first one, which was 0 base, which is 0. And now let's click this. And indeed, we have 63. So now we have something very procedural. Let's test this out. Let's go over to this feedback for each loop and changing the size of the grid right down here. We can change it there. Probably a lot more easier. Okay, you can see that the color is sticking with wherever is mapping correctly. Like the ratios are not changing. So this is super procedural now. And I use this technique a lot in order to get the topology, to change the topology of my geometry in order to help me with procedural modeling. And that's where it brings us to the next basic concept. So this one's basic concept number 4. I take this up a notch, and we'll really see this in action when we use all the things we learned throughout basic concepts 1 through 4 to make a procedural bookshelf in the next video, basic concept number 5. Thank you for watching and sticking to the end.